Okay, so we're in section 2.3 here. This is the last section in chapter 2 that we cover. And it's got two topics that we want to discuss. The first is certain properties of determinants. And what we're really working towards is one specific property that's really useful. I'm going to call it the multiplicative property of the determinant. And then after that, we're going to look at Cramer's rule, which is another way of looking at solving systems of linear equations. So we'll talk more about that when we get there. Let's focus first on this multiplicative property that we're working towards. So we're going to state the multiplicative property right here, but it's going to take a little bit of work to prove it. And what it says is that if we have any two square matrices, A and B, that have the same dimensions, the determinant of the product of A and B is equal to the product of the determinants of A and B. Now, you might look at this initially and think, well, that seems like it should be true, but you should really question why. What is it about the definition of the determinant that makes something like this true? And this is where, especially at the level of linear algebra, you have to really think about why the properties that we use in math work. And part of that is also seeing that certain properties that we might expect to work actually don't. For example, this one, the determinant of a sum of two square matrices of the same size is not equal to the sum of their determinants, at least not in general. There is a special case that we could talk about, I think your book talks about it, where this does become true, but it's not true in general. Okay, so we're going to work towards proving this multiplicative property. And to start with, we're gonna prove a lemma. So this lemma says that if B is an n by n matrix, making it square, and E is an n by n elementary matrix, then this multiplicative property works in the special case where we have E times B. So again, this looks like the multiplicative property, but we're looking at a special case where the matrix on the left is an elementary matrix. Okay. Now, in order to prove this, we have three different types of elementary matrices that we've talked about, one for each of your elementary row operations. However, we're really only going to look at one of those cases here. The other two are going to follow kind of similar steps, and it's more it's a little bit tedious and not as instructive as it might sound to go through all three cases. So Let's be specific about what kind of an elementary matrix we want to focus on here. We're going to look at the case of an elementary matrix that interchanges two rows of your identity, IN. Okay, so here's what we know about elementary matrices. If I'm looking at that specific case of an elementary matrix E, and if I multiply E to the matrix B on the left, then back in chapter 1, we showed that that does the same thing as performing that corresponding row operation on B. In other words, this product, E times B, will do the same thing as just interchanging the corresponding two rows of B. Okay? Now, in the previous section, section 2.2, we showed that if you, we showed what happens to the determinant of a matrix if you perform certain row operations on it. And one thing that we showed was that if you take a matrix like B, interchange two rows, and then take the determinant of that new matrix, what you get is the opposite of the determinant of the original matrix. Or in other words, you get -1 times that other determinant. So what that says, up until this point, what we've shown is that the determinant of EB is equal to negative determinant of B, okay? But one thing we also did in the previous section is we looked at what the determinant of elementary matrices by themselves are equal to. So we know that the determinant of this specific elementary matrix from our previous work is just equal to -1. So putting all of this together, if I looked at the determinant of E times the determinant of B, knowing that the determinant of E is equal to -1, this can be rewritten as -1 determinant of B, or just negative determinant of B. But we already established that this is what the determinant of EB would look like. And notice here we have our multiplicative property for this special case. We've proven it. Okay? Now, Again, you should remember that there are two other cases that we would need to look at, but the proof would be pretty similar, so we're going to just accept all three of those cases as true. And so this multiplicative property will work for any elementary matrix times any square matrix such that they have the same dimensions. Okay. Now, I mentioned down here that this actually establishes a more general result, because here I'm showing a product of B times only one elementary matrix on its left. But what we can do is we can actually repeat this process of essentially pulling elementary matrices out into their own determinants over and over again, allowing us to generalize this result to a product of any number of elementary matrices on the left. So here's what I mean by that. Let's suppose that instead of just a single elementary matrix, E times the matrix B, we have K of these elementary matrices times B. Okay? That means I have a total of K plus 1 matrices being multiplied here. However, if I wanted to, I could group up all but the first elementary matrix in this product here, and then just think of that as E1 times whatever matrix I get from the rest of these being multiplied. So I can actually think of this as a product of just two matrices, and applying this result allows me to take that first elementary matrix out into its own determinant, leaving me with the determinant of the remaining matrices. But I could then repeat that process using that to kind of peel out another E2 or another elementary matrix, in this case E2, into its own determinant. And I can keep doing that, just taking these elementary matrices out, again, using this property over and over again, until I get this. The determinant of that large product there is just the product of each individual determinant for all of the matrices in that product, right? So right away we get an extremely useful theorem that follows from this, which we are going to use throughout the course. This is a very, very important theorem, and it's our probably the most useful technique for determining whether a matrix is invertible or not. So for this theorem, we're stating that a square matrix A is invertible if and only if its determinant is non-zero. That would put this in our equivalence theorem. That's where it's going to end up. So to prove that, it's an if and only if proof. We have two directions to prove. We're going to let A be a square matrix. And for this first direction, we're going to suppose that A is invertible. That means the goal now is to show that its determinant is non-zero. So we already have shown in our equivalence theorem that the fact that A is invertible means that it can be expressed as a product of elementary matrices. So I can say that A is equal to E1, E2 times, yada, yada, yada through EK, where all of these are the appropriate elementary matrices that would multiply to make A. Now, since these two things are equal to each other, their determinants would have to be equal to each other. So taking a determinant of both sides tells me that the determinant of A is equal to the determinant of all of these elementary matrices, which by that previous result that we just talked about, can be represented as a product of all of these determinants here. However, given that all of these are elementary matrices, we've already shown in the previous section that any time you take the determinant of an elementary matrix, regardless of which type it is, the result is always non-zero. We can go back and, to section 2.2 and look at each individual case and show that we never get zero as the determinant of an elementary matrix. So what that means is I have a product of non-zero real numbers here, which can never equal zero. Thus, the determinant of A is non-zero. That establishes the first direction. Now we need to go the opposite direction. What we need to do is show that if the determinant of A is non-zero, then A will be singular. Sorry, not singular. It will be invertible. That's the opposite of what I wanted to say. So let's make that assumption. Let's suppose that the determinant of A is not equal to 0. And let's let R be the reduced row echelon form of our matrix A. Okay? So we can obtain that reduced row echelon form for A, this matrix that we're going to be calling R, by normally we would do it by performing Gauss-Jordan, which is a series of elementary row operations until we get to R. But we've seen since chapter 1 that the exact same thing can be accomplished by multiplying A on the left by the appropriate elementary matrices that would accomplish the same thing. So once again, I have R equals a product of elementary matrices times this matrix A. And now I can apply that result that we proved up there once again. Taking the determinant of both sides says that the determinant of R is equal to the determinant of each of these elementary matrices times the determinant of A. Now we are under the assumption here that the determinant of A is not equal to 0, which means that I have a non-zero number here times a bunch of non-zero numbers over here, because once again, each elementary matrix has to have a non-zero determinant. So that means that the determinant of R is equal to a product of non-zero numbers, which would mean it's non-zero.